Who is there online? Some more. Who is there? Just type as a hi. Who all are there? Write down the questions. Calculate the force of gravitation. Calculate and please kindly join on time. Okay. Write down. Calculate the force of gravitation. Calculate the force of gravitation between the earth and sun. Between earth and sun, comma, given that the mass of the earth is 6 into 10 raised to 24. 6 into 10 raised to 24 kg, and of the sun 2 into 10 raised to 30 kg. 2 into 10 into 30 raised to 30. 2 into 10 raised to 30 kg. Full stop. Find the average. Find the average distance between. Find the average distance between the two. Is 1.5 into 10 raised to 11 meter. 1.5 into 10 raised to 11 meter. Okay. So this is what the problem. I will read the problem once again. Calculate the force of gravitation between the earth and the sun, given that the mass of the earth is 6 into 10 raised to 24 kg and of the sun is 2 into 10 raised to 30 kg. The average distance between the two is 1.5 into 10 raised to 11 meter. Okay. So here at the beginning only they are asking us to calculate the force of gravitation. Means we have to calculate here F. Okay. Force of gravitation we have to calculate. So we know that gravitational force between two bodies. Here two bodies are earth and sun. Okay. So F is equal to, we have the formula G m1 m2 upon r square. Okay. So here m1 and m2 are nothing but sun and earth respectively. So gravitational constant, the value of gravitation constant is 10 raised 6.7 into 10 raised to 11 Newton meter kg square, per kg square. So mass of the sun and mass of the earth is also given. So this is 6 into 10 raised to 24, and mass of the sun is given 2 into 10 raised to 30. Okay, 2 into 10 raised to 30, and the distance is given between them is 1.5 into 10 raised to 11 meter. Okay, so here 1.5 into 10 raised to 11 square meter, that 11 raised to 2. So here 6.7, 6 2s are 12 into here 11, 30 plus 24 is nothing but 6 0. Okay, then 6 6 minus 11. Okay, so we have here 10 raised to minus 6 7 divided by 1.5, 2.25 into 10 raised to 22. Okay, so now do this calculation. Here we get minus 5. So now do this calculation. After doing this calculation, what will be the answer? Check. This 10 raised to 11 also you can take it up and find out the answer. We'll get this as a 35.37, okay, or 73, like that, 733 and so on, and minus 5 minus 22 is nothing but minus 27 Newton is the force between them, or 0.357 into 10 raised to minus 25 is the answer. Okay, so take a screenshot. Here everything is given very clearly. So I started with very basic problem. Okay, so very basic question from this chapter. Okay, now write down the next question. Take a screenshot. So here write down the next question. Find the gravitational potential. Find the gravitational potential at the site of the geostationary. This is at the site of geostationary satellites. At the site of geostationary satellites, full stop. Assume the height of the satellite to be 4,200 kilometer, 4,200 kilometer from the center of the earth, and mass of the earth is given. Mass of the earth is 6.0 into 10 raised to 24 kg. Mass of the earth is 6.0 into 10 raised to 24 kg. Okay, so I will repeat this question one more time. Find the gravitational potential at the site of geostationary satellite, full stop. Assume the height of the satellite is to be 4,200 kilometer from the center of earth. Okay, so here we have to find out the potential, not potential energy. We have to find out the potential and potential of the gravitational satellite or geostationary satellite. Here height of the satellite height of the satellite is to be 4000 kilometer from the center of the earth. Means its height is given, means the satellite is at certain height from, we are measuring the distances from the center of the earth, and that is given 4200 kilometer from the center of the earth. So I will here draw the diagram. Okay, here I will draw the diagram. Check. Here we have this as a earth, okay, and this is the center, and we have this as a radius r of the earth, and somewhere satellite is here, and from the center of this earth to this distance is nothing but 4000, how much, 4200, okay, this is nothing but what, 4200 kilometer, okay, this is what the distance given. Okay, so here in short we can say that r plus h, okay, because from the surface of the earth the satellite is at h height, but here combined height is given, so we can write r plus h is nothing but 4200 kilometer, that is 42 into 10 raised to 3 kilometer, okay, or you can 4300 into 10 raised to 3, 4200 into 10 raised to 3, or we can write 42 into 10 raised to 5, 5 kilometer. Okay, this is nothing but your r plus h. We have to find out the gravitational potential. So potential, we know that V is equal to Gm upon r. So but here r plus h means entire distance is there, r plus h, then substitute the values over here. G is nothing but 6.7 or 6.67 into 10 raised to minus 11 into mass of the earth is given here, that is 6.0 into 10 raised to 24. 6.0 into 10 raised to 24, and r plus h is given 42 into 10 raised to 5. Okay, so simplify this. So here 7, 6 ones are 6, so it is 7. So 6.7 by 7 into 10 raised to here 24 minus 11 is nothing but 3, 1, 13, 13 minus 5. Okay, so 13 minus 5 is nothing but, we can write it as here 8. Then you can do this division. After dividing this, you will get potential as a 9.5. 9.528 into 10 raised to, you will get 10 raised to 6 if you adjust the decimal. Okay, 6. Then potential, here we have joule per kg. Okay, so this is what your answer for the potential for the geostationary satellite. Getting this? Okay, everything is given, very simple problems. Copy this or take a screenshot. Don't make a mistake in radius. No need to add here radius because this height is given from the center of the earth. Okay, so copy this. Krishna, are you there? Krishna, or who, Rujul is there? Okay, chalo, write down the next problem. Write down next problem. Assuming the earth to be sphere, assuming earth to be sphere of uniform mass density, comma, how much would a body weight halfway halfway down to the center of the earth, to the center of the earth, if it is weighted 250 Newton on the surface, 250 Newton on the surface. I'll repeat. Assuming the earth to be sphere of uniform mass density, how much would a body weight halfway down to the center of the earth if it is weighted, weighted, weighted 250 Newton on the surface. Okay, so here they are asking the weight. Okay, weight component of that body they are asking, and the question is that earth is to be, we have to assume it as a sphere, and that sphere is having uniform mass density. Okay, so how much would the body weight? The body weight is how much? Halfway down to the center of the earth. Okay, that means here h is nothing but what? R by 2. Okay, so here I will try to draw the diagram and I will try to explain. So here we have here, this is the earth. Okay, having the radius is nothing but what? R. Okay, and the body, initially body is at the surface, so in that case its mass or its weight is acting, the W is equal to mg, acting vertically downward. Okay, weight is what? Acting vertically downward, and that weight is given how much here? 250 Newton. Okay, that is given 250 Newton, and as this sphere is having uniform mass density, and then that body they bring it to the half the way of the radius of the earth. So this will become how much? R by 2. They brought body and kept in between the radius. Okay, exactly mid of the radius, because they are saying halfway down to the center of the earth. Okay, so this much is given, and we know that whenever we are bringing the body at certain depth, so gravitational acceleration due to gravity g is nothing but g dash is equal to g inside the bracket 1 minus h by r. Okay, so I will write g 1 minus here r by 2 upon r. Okay, so r and r get cancelled. G 1 minus 1 by 2, that is nothing but what? G by 2. This is nothing but acceleration due to gravity when you bring that body at certain height. Okay, but here we know that acceleration due to gravity. Okay, so if I multiply here on both the sides, because weight component is given and they are asking, they are not interested in g dash, they are asking in how much is the weight. So multiply on both the side is how much? By m. So you will get mg dash is equal to m into g, okay, divided by 2. So m into g, that component is given how much here? 250 no? By 2, that is nothing but here we will get it as 125. Okay, we will get 125 Newton is what the weight we are getting. Okay, so little bit different question, but this is what the answer. They are asking weight component, and mg dash is also a new weight component when you brought the body at the center of the earth, that is r by 2. Copy this. Finished? Then write down next question. Newton's universal law of gravitation. This is MCQ question. Newton's universal law of gravitation applies to Newton's universal law of gravitation applies to first both small and big bodies, both small and big bodies. Second, only valid for solar system, only valid for solar system. C, planets only. D, small bodies only. D, small bodies only. Okay, so here I will repeat this. Newton's universal law of gravitation applies to first both small and big bodies. B, only valid for solar system. C, planets only, and D, small bodies only. Okay, so you have to find out the correct option. So basically we can apply for both small and big bodies. Okay, so option A is the correct option, because here Newton's law of universal gravitation states that two bodies in the universe attract with each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So it is applicable both in smaller and bigger bodies also. Okay, in planets also, even in solar system also, there is a universal gravitation law is also applied. In that case, we are taking sun and planet, okay, as a two masses. So of course there is also what a gravitational force is there. So here the correct option is option A, that is for both small and big bodies. Okay, so tick mark that answer. Write down next MCQ. If the earth is at 1/4, if earth is at 1/4 of its present distance, if the earth is at 1/4 of its present distance, 1/4 of its present distance from the sun, comma, the duration of the year will be, the duration of the year will be, first option given, first option write down 1/8 that present year, 1/8 the present year. Second option 1/6 the present year. C 1/10 the present year. D half the present year, half the present year. So I will read one more time. If the earth is at 1/4 of its present distance from the sun, the duration of the year will be first 1/8 the present year, 1/6 the present year, 1/10 the present year, half the present year. Okay, so these are the options are given. So how to get this answer? So can we apply here to get this answer? See, they are asking calculations are also here, and they are asking duration of the year and how much distance it sweeps. So from the Kepler's third law we can solve this question. So Kepler's third law says that time period t square is directly proportional to the what? Radius square. Okay, so here we can apply that same formula here, third law. Okay, here we know the formula, t square is directly proportional to r cube. Okay, so we can take time period for these both things. T1 by T2 square is equal to, we have r1 square upon, sorry, r1 cube upon r2 cube. Okay, this is what we can write, and they are saying here 1/4 of the revolution. Okay, so here what we can do, so we can keep the radii of these two planets will remain same, and this is how much, 1/4, no, correct, 1/4 of the radius, that is r by 4 raised to 3. So here r get cancelled and 4 will go up into 3. Okay, we will get this much. So here this is nothing but T1 by T2 whole bracket square is 4 cube we are getting. If I take a square root on both the sides, then I will get 4 raised to 3 by 2. So I am taking square root on that side also. So here 4 is nothing but 2 raised to 2 and whole bracket raised to 3 by 2. These powers are get multiplied, 2 into 3 by 2, 2 get cancelled and 2 raised to 3. That is nothing but 8 years. Okay. So we are getting here answer 8. They are asking time period for the second. So I am getting T1 by T2 is this much. So they are asking T2. So T2 is nothing but T1 by 8. This is nothing but what, the answer. So check which one is the correct option here. Option A. Option A, 1/8 to the present year. This is the answer. Finished? Okay, write down one more question, MCQ. In a planetary motion, first beat, the total angular momentum remains constant. Second, the linear speed remains constant. The linear speed remains constant. Third, neither the angular momentum nor angular speed remains constant. D, last bit, the angular speed remains constant. Last option, the angular speed remains constant. So I will repeat this question. In planetary motion, the total angular momentum remains constant. B, the linear speed remains constant. C, neither the angular momentum nor angular speed remains constant. And last, the angular speed remains constant. Okay. So here we have the planetary motion. Okay. So in planetary motions, so this kind of questions we can solve by using Kepler's law or Kepler's law of planetary motion. And what Kepler's law says that all moves or all planets are moving about around the sun in an elliptical orbit, having sun as a one center or sun as a focus. Okay. And another is what, the radius vector joining any planet, they sweeps equal area in a equal intervals of a time. So these are the two laws we know that. So from this we can conclude, because we put there we substituted V is equal to R omega. So the total angular momentum will remains constant. Okay, according to the third law, they are what, sweeping equal areas in the equal intervals of a time. whether the sun is at as the elliptical orbits are there and there are two axes, one is major and minor axis. So people think that if it is the planet is away from the sun, then it covers more area. If it is near to the sun, then it covers less area. That is not the thing. It sweeps equal area in equal intervals of a time. So according to that, the option A is the correct option. The total angular momentum will remain same. Okay. So write down option A. Tick mark. Write down one more MCQ. The value of a G, small g, is at a particular point, is 9.8 meter per second square. 9.8 meter per second square. Suppose the earth suddenly shrinks. Suppose the earth suddenly shrinks uniformly, to half its present size, without losing any mass, full stop. The value of a G, at the same point, and inside the bracket they gave information, assuming that the distance of the point from the center of the earth does not shrink, will become first one. Options are given: 9.8 meter per second square, 9.8 meter per second square. B, 4.9 meter per second square, 4.9 meter per second square. C, 19.6 meter per second square. And last option, 2.45 meter per second square. Okay. So I will repeat this question. The value of a G at a particular point is 9.8 meter per second square. Suppose the earth it suddenly shrinks uniformly to half its size, present size, without losing any mass. The value of a G at the same point. Okay, what will be the assuming that the distance of the point from the center of the earth does not shrink, will be, they are asking the value here. So here we know that acceleration due to gravity. Okay, acceleration due to gravity, we have G is equal to Gm by r square. Okay, we have this acceleration due to gravity is Gm by r square. This derivation we have, where here is the mass of the earth and r is the separation between both the masses. That means that body is somewhere on the surface of the earth. Okay, so suppose this is a mass of the this is the surface of the earth, and suppose here one mass is kept small m. Okay, so here the masses, the r is the separation between the masses and the volume is reduced, keeping mass and separation between these two bodies will remain same, that will not change. Okay, as the body is what means mass of the earth is shrinking, sorry, not mass of the earth is not shrinking, whole universe is what started shrinking, but the gravitational acceleration due to gravity will remain same everywhere. Okay, so its answer will come 9.8 into 10 raised to 9.8 meter per second square. Option A will get. Okay, we'll get the answer 9.8. Okay, now write down one more point, one more question. The mass of the earth is 81 times, the mass of the earth is 81 times heavier than the moon. The mass of the earth is 81 times heavier than the moon, full stop. Its diameter is about 4 times larger than that of the moon, full stop. Estimate the value of acceleration due to gravity on the surface of the moon. Okay, so this is also very important question. So I'll repeat, mass of the earth is 81 times heavier than the moon. Its diameter is about 4 times the larger. Okay, 4 times larger than that of the moon. Estimate the value of acceleration due to gravity on the surface of the moon. Okay, so here the body, any body is having mass small m. Okay, so capital M we are taking is the mass, and that capital M is the mass of the moon. Okay, and small m is the mass of the earth we can take. Okay, or else you can, if you want, you can take this mass as a earth. Mass of the earth is m, and capital small m we can take the mass on the moon. Okay, so mass, then radius of this earth is also r, and radius small r of the moon. Okay, we assume this, and here they are saying in the first statement, mass of the earth is what? 81 times heavier than the mass of the moon. Okay, so according to the statement, capital M equal to 81 into m. This relation we got, and of course the diameter is also given. They are saying its diameter is about 4 times larger than that of moon. So d is equal to 4 times of small d. So we are not dealing with diameter. We want the answer in terms of radius. So here twice the radius is nothing but diameter. 4 into twice the radius. Okay. So here 2 and 2 get cancelled, and radius we will get it as a 4r. Can you getting? So from this we got the relation r is equal to 4 times of the r. So they are asking acceleration due to gravity at the moon. Okay, we are interested in gm, that is acceleration due to gravity at the moon. So here we can use the formula. On the surface of the earth, acceleration due to gravity ge is nothing but gm upon what? r square. We can write. And on the surface of the moon, okay, acceleration due to gravity is gm upon r square. Okay, so this is nothing but small m. Okay, now divide these equations. So if you take this as a 1 and this as a 2, now divide both the equations, so you will get some relation. GE upon GM is equal to GM upon R square, and here you will get G small m upon small r square. GG get cancelled. So here m upon r square into r square by m. So after reciprocal we are getting the answer like this. So here we can calculate the answer for first GM. We are interested in GM. So you can just rearrange the term. GM is nothing but GE into small m into r square. Okay, small m into capital R square upon capital M into R square. So now substitute the value, many things are get cancelled. We got capital R is nothing but 4 times of R. So you can substitute here. So GE into small m, and here 4 times of the R square upon R square. So this R square get cancelled. 4 4s are 16 ka square, means 4 square is nothing but 61. Okay, and meanwhile mass we got it as 81 times. So here this mass is nothing but 81 times, we can write here. So GE gravitation on the surface of the earth is nothing but 9.8. okay, 9.8, and mass of the earth is 6 into 10 raised to but mass is also get cancelled, no, with small m. This and m is get cancelled into 16 divided by 8. So if you do the calculation, you will get mass acceleration due to gravity on the surface of the earth is nothing but 1.94 meter per second square. This is nothing but what? Mass. This is nothing but acceleration due to gravity on the surface of the earth. Getting this? So this is little bit assumption wala question. So copy this or take a screenshot. Getting this question? I covered few questions from this chapter. Check once. I took some numericals and some questions. Getting this, how I assumed mass and how I obtained the relation between diameter and mass and how I substituted. So this kind of questions mostly they asked in the exam. Are you getting these questions? Now write down one more question. Last question. Write down. MCQ is there. A missile is launched with velocity less than the escape velocity, full stop. The sum of its kinetic and potential energy is. The sum of the potential and kinetic energy is. First option positive, second option negative, third option 0, last option may be positive or negative. May be positive or may be negative. Okay, so I will repeat this question again. A missile is launched with a velocity less than the escape velocity. The sum of its kinetic and potential energy is first positive, second negative, third 0. D may be positive or may be negative. Okay, so we already find it out the total energy of the satellite, and sum of kinetic and potential energy is nothing but what? Total energy of the system. And we are getting their total energy, we got it as a negative. Okay, so answer is B option, answer is negative. Velocity, velocity less than the escape velocity of the missile, and it is bounded to the gravitational field of the earth. Okay, so we are getting there, negative is the answer. Finished. So next part I will cover by tomorrow. I covered as much as questions. Okay, thank you. I will end this meeting.